Hello there. So I posted a video recently of a patch dealing with microtonal tuning. And I just wanted to show you how easy it actually is to work with different tunings in pure data. But first, a short historical note. The most commonly used tuning in the Western European tradition is the 12-tone equal temperament tuning, which means that in this tuning, the octave is divided into 12 equal steps, with each semitone being equally distant from its neighbors, which allows for melodies and harmonies to be played in every key, and in all the keys they would sound the same. Before 12-tone equal temperament solidified as the default tuning system for Western European music around the 18th century, there was a bunch of other different tuning systems based on simple whole number ratios for the intervals. And that actually means that in these systems, not all the semitones in an octave would have equal distance from one another, and that means that some keys would sound different from the rest. Like you couldn't just transpose a piece from, say, C major to D flat major without retuning the entire harpsichord or whatever. So, as you know, making electronic music with the computer, we often deal with the MIDI protocol, which is a protocol defining musical notes across platforms. It assigns numbers from 0 to 127 to each note, and it is based on the 12-tone equal temperament tuning system, because by the time MIDI notes came to be, the 12-tone equal temperament system was considered to be a default system, and like most of the composers were using it. Anyway, let's get to patching. Yeah, here I have a simple synth that I made. Everything except for the keyboard object, which is from the else library, is in vanilla, so you can copy this patch and follow along if you want. And here is my little synth. It's really basic, but yeah, you can copy this as well. Or try your own synth if you have one ready. Anyway, in pure data, we have an object that is called M to F, which is a MIDI to frequency object. It converts MIDI notes to frequency to feed into, in our case, the phasor object, or just any oscillator you got. So yeah, I'm going to connect everything. And we can see that it converts these whole numbers into frequencies. But what kind of conversion formula does this object actually use? And the formula looks like this. As you can see, the frequency in hertz equals to 440 multiplied by 2 to the power of n minus 69 divided by 12. So I'm going to rewrite this inside pure data and explain every term in this formula. So instead of M to F, I'm going to write expression. Then we're going to have 440 multiplied by power 2 $f $f1 minus 69 divided by 12, and don't forget the bracket. Now it works exactly the same. And here 440 is the frequency for the middle A, because it's a whole number in 12-tone equal temperament, and it's a middle A over here. We're going to try changing different terms in this formula, and I suggest we start with that 440 for middle A. We can fine-tune it if you want to. Now it's in tune for modern big band, and we can do something weirder, like 254. As you can hear, it's all still in tune, because we still have the same tuning, but we have a different point of reference. So it's transposed to some random frequency, specifically 254 Hertz in our case. Anyway, I'm going to remove this term altogether from the equation and show you how to make a pitch bend using the information we've got now. So I have the clone object for the synth. I have to open it, create a new inlet, going to create a message to a line object here. And then after the unpack, I'm going to create a multiply object and connect it to our phasor here. So now we have to save it. And now our clone object has a second inlet to the right. We're going to create another message here and write all $1. And since I don't have any knobs or sliders on my MIDI keyboard, I'm just going to create a slider in here, divided by 127, but then multiplied by 440. and add another 440. So we're back to middle A. I have to click on it. Yeah, we're back in our original key. And now if I press a chord and do this, we get the pitch bend. It goes all the way to the octave, because octave has the ratio of 2 to 1, meaning that if this A is 440, then the A up an octave is going to be 880 in here. Anyway, so this is the pitch bend. Let's check the other terms of the equation. So as you understand, 69 is just to bring our MIDI notes to the point of reference. So as you can see, if I press 69, now the equation outputs 1, and we multiply that by 440 inside of our synth here, and we just get 440 as a base frequency. If we play a note octave lower, we get half of that number, so 220. Then, yeah, this is the fun part. As you can see here, we divide our variable by 12, and you can change this number to something else, for example 9. Now I'm going to write something here to transpose everything. This is the frequency of middle C. Wait, it didn't work. Let me do more adjustments. Yeah, now it's a C. Now we get a new really interesting scale here. As you can see, we still have octaves equal. They're just smaller. They have only 9 tones between them instead of 12 as before. I should stop playing that while I speak. Yeah, you can go crazy with this number. Every interval inside are smaller than a semitone. And the octave is actually wider, as you can see on the keyboard. Yeah, so this is one thing we can change. The other thing is this number. 2 is the ratio for the interval of the octave. So every time we move up an octave, the frequency doubles, as you can see here. It's 1, then 2, then 4 in the output of this equation. So it doesn't necessarily have to be an octave. It can be a ratio of a perfect fifth, which is, I think, 1.5. Yeah, so now we've got perfect fifths and 12 tones that fill it. That sounds like this. And this is kind of the fun part, because every time you go through all the 12 tones of our tuning, you don't end up on the pitch that sounds the same, because it's not an octave, it's the fifths. So instead of having C, then, well, another C somewhere here, we just have C, then G, then D, and it kind of opens things up a bit. And yeah, you can experiment a lot with just changing these things to some really random, arbitrary numbers and trying to find the sonorities you like. Yeah, I think it's a lot of fun.